We are now discuss work and energy. Okay, so work, let's define work. Okay, work done on an object by a constant force is given by this equation. So that, say for example, a certain object is acted upon by a force. And because it is acted upon by a force, there is a tendency that an object will move from one place to another, or there will be displacement because of that application of force. Say that displacement is represented by delta x, so that the work done on the object is just equal to the magnitude of the force times the displacement. Okay, so again, F here represents the magnitude of the force and delta x is the magnitude of the displacement. Okay, now the SI unit that we usually use for work is in joules. So joules is equal to Newton times meter, or Newton meter. Okay, or that is equal to kilogram meter squared per second squared. Okay. Now, this work, okay, is work by a constant force along the displacement. So say our force, the action of the force is parallel to the displacement. But what if the force is applied to a certain angle or is inclined? Okay, so that the work W done on an object by a constant force F is given by this formula. Okay, so say this is again the object that is acted upon by a force F, but this force F is inclined such that its line of action is not parallel to the displacement. Okay, so that what we do here is we have to get the component of this force, its component along the axis of the displacement. And that will be, say, the angle of that force from the horizontal is theta, so that its horizontal component, which is parallel to the displacement, is F cosine theta. Okay, so that the work done of the object, okay, is equal to the force times the displacement, but we make sure that this force is the force parallel to the movement or to the displacement. Okay, so that in this situation, for the force that we multiply to the displacement is the force that is parallel to the axis of the displacement. So we use F cosine theta times delta x. Okay, so this is work done on the object if the constant force is at a certain angle. Okay, and the SI unit is still in joules. Let's have an example about work, or let us apply this principle of work in this first example. So example number 1, an Eskimo returning from a successful fishing trip pulls a sled loaded with salmon. The total mass of the sled and salmon is 50 kilograms. So this is the sled and then this is the salmon. The total mass is 50 kilograms. And the Eskimo exerts a force of 120 newtons on the sled by pulling on the rope. So there is a rope here in the sled. Okay, so the force of pulling force is 120 newtons applied by this Eskimo. Okay, first question is, how much work does he do on the sled if the rope is horizontal on the ground, or theta is equal to 0, and he pulls the sled 50, or rather 5 meters. Okay, so this is now the sled. Okay, and then we have here salmons he collected. Okay, so that the total mass as stated in the problem is 50 kilograms. Okay. Now, there is a rope here. First question is, if the rope is, application of the rope is horizontal, or the rope is horizontal, so that the force 120 Newton applied on the rope is also along the horizontal. Okay. And then, the displacement was given to be 5 meters. Okay. Now, the work done is equal to all forces along the displacement times the displacement. Okay, so that the only force that is parallel to the displacement is this 120 Newton pulling force. So we'll have 120 Newtons times 5 meters. And that will be, okay, 120 times 5. So 600 Newton meters or 600 joules. Okay, so this is for first question A. Okay, next is letter B. How much work does he do on the sled if theta is equal to 30 degrees and he pulls the sled the same distance? So this time, okay, the rope is now applied 30 degrees from the horizontal. Okay, or theta is now horizontal. Theta is now 30 degrees from the horizontal. So still we have here 50 kilogram load. Okay, so the same displacement as stated in the problem. Therefore, our work done is the horizontal component of the pulling force. So that is 120 cosine 30 times the displacement because of the force. Then that is equal to, okay, $519.62. That is in joules. Okay, so let's check if we got it correctly. Okay, so that's around 520, so we're correct. Letter C is, suppose the coefficient of kinetic friction between the loaded 50 kilogram sled and snow is 0.2. Find the work done on the sled by the friction. Okay, only, so this work done is only by the friction. And the net work if the skimo again pulls the sled 5 meters, exerting a force of 120 newtons at an angle 0 degrees. Okay, so on letter C, there is already coefficient of friction between the sled and the snow, and that is 0.2. Okay, kinetic friction. So that we have a normal force, and then we also have, of course, we already have frictional force, which is equal to the coefficient of kinetic friction times the normal force. Okay, we use kinetic coefficient of friction because of the pull on the rope, there is already movement, okay, on the sled. So this is again 120 newtons. This where theta is said to be 0. Okay, so again the displacement is still 5 meters, right? So the work done by the friction, okay, that is equal to, okay, we have mu, which is 0.2, and then the normal force. If we are going to sum up forces vertically, then normal force is simply equal to the 50 kilogram load, where we have to multiply it to the gravitational acceleration of 9.81 meter per second squared to convert it to newtons. Then this is now the friction force, which is parallel to the displacement. Okay, so this is the friction force. Okay, and then the displacement is again 5 meters. So the work done only by the friction is, okay, so we'll have 0.2 times 50 times 9.81 times 5. Okay, we have 490.5 joules. Now see, our friction force, even if it is parallel to the displacement, it is opposite the direction of the displacement. So since it's opposite the direction of the displacement, we will use friction force as a negative force. Okay, so therefore this gives a negative work on the object. Okay, so that the net work done on the object, okay, which was also asked in the problem, wherein we now consider the force 120 newton on the rope at an angle 0 degrees. Okay, so we'll have, okay, force along the displacement will be the 120 newton, okay, minus that of the friction force, which is 0.2 times 50 times 9.81. Okay, so this is the friction force, right? Then this net force, this is not the net force. Okay, then we now multiply the total displacement of 5 meters, so that the net work applied to the object or done on the object is, we'll have 120 minus, we'll have 0.2 times 50 times 9.81. Okay, then times 5 displacement, so that will be 109.5 joules. Okay, next we'll have the last question. Okay, the same condition as this one, but this time, okay, the one we repeat the calculation, but this time the applied force is exerted at an angle of 30 degrees. So that's for our last question. So again, we have the sled, then we have the, it is 50 kilograms in mass. So we have the normal force and then the friction force, and then the rope is now 30 degrees from the horizontal, and still our displacement is 5 meters. Okay, so that the net work done on the object would be, okay, the net force for the 120 newton pulling force, we will use, or we'll have to get its horizontal component, this because this is the component of the force, it is parallel to the displacement. So since it's along the direction of the displacement, then we'll take it as a positive force because it gives a positive work, 120 cosine 30. And then another force along the displacement, but this one is opposite the direction, so we'll take it as a negative force, which is the friction force. 0.2 times the normal force, which is just equal to the 50 kilogram mass, is 50 times 9.81, then times the coefficient of kinetic friction. So this is now the net force times a displacement, again, of 5 meters. Okay, so we'll have 20 cosine 30 minus 0.2, 50 times 9.51. Okay, we'll have times 5, and that will be got a little mistake here. Okay, so when we have to repeat calculation here, we have to first get the work done by the friction. So let's just remove this one. Okay, so work done by the friction. Okay, so again we'll sum up forces vertically, so upward forces positive. Okay, so we'll have the normal force minus the weight, which is 50, times 9.81, then plus the vertical component of the 120 Newton force. So we'll have plus 120 sine of 30, so that the normal force is equal to, you have 50 9.81 minus 120 sine of 30. Okay, so that the normal force is equal to 430.5 newtons. Okay, so that the friction force will now be equal to the coefficient of kinetic friction times the normal force, and that will be 86.1 newtons. So that the work done by the friction is equal to negative 86.1, negative because friction force is opposite the direction of the movement or displacement, then times again 5 meter displacement, so that will be negative 430.5 joules. Okay, then we will now solve for the net work. Okay, so for the net work, now have the total force, so force along the displacement, positive for the 120 Newton force. Okay, and then what else? We have friction force. This is also along the displacement, so but it is opposite the direction, so we have minus friction force is 86.1 newtons as calculated beforehand, so this is 86.1. This is now our net force times the displacement of 5 meters. So our net force for this case will be, okay, so we have 120 cosine of 30 minus 86.1 friction force, then times 5, So that will be 89.12 joules. Okay, so this is how we solve for work done on an object. Okay, let's proceed. Okay, next is we'll have kinetic energy and work energy theorem. So the kinetic energy of an object of mass m moving with the speed of v is defined by ke equals 1/2 mass times velocity squared. So, due to the velocity of a certain object with mass m, there is kinetic energy produced on that object. And that is what you call kinetic energy, and it is equal to 1/2 mass of the object times velocity of the object squared. Okay, so the unit for kinetic energy is still in joules because that is in kilograms times meter squared per second squared. Okay, now we now arrive at an important result known as the work energy theorem, so that the net work done on an object is equal to the change in the object's kinetic energy. Okay, so the final kinetic energy minus the initial kinetic energy, or rather delta ke, or the change in the kinetic energy of an object, is the network done on the object. Okay, so if that is the case, say we have this illustration now, because there is a net force applied on this object and it had the tendency to be displaced. So say in the starting point we have our initial velocity of VO, and at the final point we have our velocity represented by VF, so that the net work done on this object is equal to 1/2 mass of the object m times final velocity v squared minus 1/2 times m times initial velocity vo squared. So you see the network is the final kinetic energy at the final point minus the kinetic energy at the initial point. Okay, so let's have an example regarding kinetic energy and work energy theorem. So here the driver of a 1 times 10 raised to 3 kilograms, or that is the mass of the car is 1000 kilograms. Okay, then traveling on an interstate at 35 meters per second. Okay, nearly 80 miles per hour, slams on his brakes to avoid hitting a second vehicle in front of him, which had come to rest because of congestion ahead. After the brakes are applied, a constant friction force of 8 times 10 cubic 10 raised to 3 newtons, or that's 8,000 newtons, acts on the car. Okay, ignore air resistance. Okay, first question is, at what minimum distance should the brakes be applied to avoid a collision with the other vehicle? Okay, so for the vehicle, this vehicle has a mass of 1000 kilograms, stated in the problem, and that its initial velocity is 35 meters per second. Let's say that's our VI, initial velocity of the car. Now, it has to apply its brakes, so that we'll have here, okay, there's a car ahead. Okay, he has to apply the brake so that it won't be able to collide or hit the second vehicle in front of it. Okay, so it has to come to rest at this point. Okay, so it has to be able to stop at this point because to avoid hitting the car ahead of it. Okay, so say this is now the displacement of the car. Okay, now with the application of the brakes, there was a friction force produced, so that is equivalent to 8,000 newtons. Okay, okay, what should be the minimum distance that the brakes must be applied? So say this is the point where it applies its brakes, and this is the point where it has to come to rest or stop because there is a car ahead. Okay, this is now the minimum distance where it has to apply its brake so that it won't be able to hit the second vehicle. Okay, so that we have our net force is equal to the change in kinetic energy of the object. So here, the velocity is 0. Okay, so that the net force is equal to, you have the initial, or rather the final kinetic energy at the final point minus kinetic energy at the initial point. Okay, now for the final point, the kinetic energy is definitely 0 because there is no velocity at this final point. Okay, next, kinetic energy on the initial point. So we have 1 half times mass of 1,000 kilograms. Okay, then times the velocity. Okay, that is 35 squared. Okay, so we have 1 half mv squared. Okay, so that the net work done using this formula is equal to, okay, 1 half times 1,000 times 35 squared. So that will be negative 612,500 joules. Okay, next. Okay, now we all know that net work is also equal to the force applied, net force applied on the object times its, or times the displacement because of that net force. So since we already got the value of the net work using this formula of the change in kinetic energy, then we will equate this, no, the negative 612,500 joules is equal to the net force, and our net force, okay, all the forces along the movement, okay, is only the friction force, and we take it as a negative force because it is against the motion. So we have negative 8,000 newtons times the displacement of delta x. So this is the minimum distance of applying the brakes, delta x. So therefore, delta x should be equal to, okay, divided by 8,000. That will be 76.56. Okay, so this should be the minimum distance that the brakes should be applied to avoid collision of the car ahead. Okay, next question. If the distance between the vehicles is initially only 30 meters, at what speed would the collision occur? Okay, now we have found out that the brakes should be applied at a distance of 76.56 meters to avoid collision. But the second question says that if the distance between the vehicles is initially 30 meters, therefore if it will apply the brake 30 meters behind the second vehicle, then it will really be able to hit the second vehicle. Okay, so if the distance ahead was 30 meters, okay, then we have to get the speed where the collision occurs. Okay, so that this is the initial point, then this is the point of collision of the cars, and then we have the distance that is 30 meters. So in the initial point, the initial velocity is 35 meters per second, and at the final point, velocity is unknown. Okay, velocity at the point of collision. Okay, and still mass is the same, 1,000 kilograms, and the friction force produced due to application of brakes would still be 8,000 newtons. Okay, so for us to get the point of collision, we have to first get the network, so that the network on this situation will be equal to force negative 8,000, the force that is the only force that is parallel to the displacement. It's 8,000 newton friction force. We take it as negative because it's opposite to the direction of motion. Then times the displacement, which is now 30 meters. So we'll have it as 8,000 times 30. That will be 240,000, or rather negative 240,000 joules. Okay, so this is the net force. The network that we used formula is the force times the displacement. Now we will use the network equals the change in kinetic energy. So again, this is our initial point and this is our final point. Okay, so for network, it's negative 240,000. Okay, so we have for the final point of 1/2 mass of 1,000 times v squared, velocity being unknown at this point of collision, then minus 1/2. We have mass times velocity. Initial velocity is 35 squared, so that v is now equal to k. By calculator, we'll try to use shift solve. Okay, let's say our x is the v squared. In the calculator, x represents v squared. Okay, then we have minus 0.5 1,000 times 35 initial velocity squared. Okay, so we'll have shift solve 745. So v squared is equal to 745, so that v is equal to square root of 745. That will be 27.29 meter per second. So if the brakes were applied 30 meters, okay, 30 meters behind the second vehicle, then there will really be a collision between the two, and that the velocity at the point of collision is 27.29 meters per second. Okay, that is all for our work energy, but we only covered work energy theorem by force times displacement, and work energy theorem by change in kinetic energy. We will continue potential energy and gravitational work on our next lecture.